well. And let's continue our discussion of transport layer. And in the last lecture, we started the last topic of transport layer, which was the congestion control, and obviously we will move towards the study of TCP congestion control. But before that, just a very quick brief recap. Before that, we discussed that to deal with the problem of congestion control, we must deal with the problem of bandwidth allocation. That's why before moving to the congestion control and TCP congestion control and the algorithms and techniques that TCP use to solve the problem of congestion control, we decided to discuss the topic of bandwidth allocation, and we started discussing an algorithm of bandwidth allocation, which was AIMD algorithm. And I, said some very important sentences which I would like to repeat in this brief recap. The first one was that the problem of congestion control boils down to the problem of bandwidth allocation, and then in the next slide we saw that the bandwidth allocation should be fair and efficient. So the sentence that I said was that the problem of congestion control boils down to the problem of fair and efficient bandwidth allocation. Okay, we want to have a bandwidth allocation algorithm that gives us something like this. This should be the solution that the algorithm give us, and we will see that AIMD, if all the devices running on the internet run AIMD algorithm, they will reach to a solution which will be something like that. So basically the sender will adapt concurrently and continuously. Okay, so all senders will adapt concurrently and continuously, based on their own view of the network, and this adaptation will be such that the overall usage of the network will be fair as well as efficient, because these are the two required things. This is the mantra of bandwidth allocation, that we want the bandwidth allocation to be fair and efficient. Okay, right. And then we saw certain allocation models of bandwidth, certain bandwidth allocation models. We said we divided the bandwidth allocation models into three categories. One of the category was that whether the bandwidth is allocated before the use, or right during the use, when it is being used, when the connection is being, so before the establishment of connection, or during the time of the connection. So it was called open versus closed loop bandwidth allocation, and we saw that in the circuit switching scenario, the open loop bandwidth allocation can be used, but since internet is a packet switch network and TCP usually adopt this, internet is packet switching, and in packet switching you can do open bandwidth allocation. You can reserve bandwidth before use, but generally what TCP does is that it use feedback to infer the network condition. Okay, and then the second category of allocation model was that who enforces this allocation, whether host does this on its own or the networks will support it. Obviously the best method is that the network support the bandwidth allocation, because I created a toy scenario, and I gave this example to you guys, that the onset of congestion is at the network devices itself. So the routers and the layer 3 packet switches, they are the one who actually sees congestion, as it is happening. So they are the one who are handling those queues, and when those queues are getting filled up and the queuing delay is increasing by leaps and bounds, then this is what we call the situation of internet congestion. So obviously the one who is experiencing is the scenario is the one who is in the best condition to deal with that scenario. So network support is the best method. Okay, and obviously there are two methods, two approaches. One is end-to-end approach, and the other one is network assisted. So network assisted, this is the best method, but this require explicit support from routers. So routers should send ECN bits to each and every host, telling them to either slow down or telling them their correct rate to transmit. But TCP, what TCP does is that TCP follows this end-to-end congestion control technique, and this is in this TCP, basically in this scenario TCP is host driven, so it is closed loop and host driven, and it is in the third allocation model category. It is not rate based, it is Windows based. So TCP is closed loop, host driven, and window based allocation model. Okay. The third category just says that how is the allocation expressed. So if you want to divide the, if you want to allocate the bandwidth to each and every sender, then I mean how you express that rate. In my toy scenario, in the last week, I just represented the rate on r by 2, r by 2, but actually what TCP does is that TCP represents this rate in window size. And we have already discussed the concept of window size when we discussed the GBN and SR protocols, pipeline protocols. Okay. How we can get feedback, these are the methods. We will discuss more about these methods in after the discussion of AIMD. I explained them on the last week as well, but we will discuss more about it after AIMD. So I started discussing AIMD and then obviously the lecture time was up. So let's continue our discussion from here. So AIMD has two parts. It's an algorithm, and it's a bandwidth allocation algorithm, additive increase, multiplicative decrease. And the two parts says that first you will additively increase the rate while the network is not congested. So it's actually like that the senders, they don't know, they don't see the network, they don't know the network condition at any particular time, but they want to infer the condition. So how they can infer the condition is that they keep increasing their rate in a very careful manner. So that is why the increase is additive. The increase is not multiplicative decrease. By the multiplicative increase. By the way, you can try as a homework for yourself, and you will see that there can be other variants of the algorithm, but they will not converge to a fair and efficient bandwidth allocation. So you can try those variants by yourself at your home. For instance, multiplicative increase and multiplicative decrease, or let's say additive increase and additive decrease. Okay, or let's say multiplicative increase and additive decrease. So all these three variants, you will see that all these variants will fail to achieve a fair and efficient bandwidth allocation, and only this one, only the AIMD algorithm, if we increase the rate additively, and in the case of congestion, if we decrease the rate multiplicatively, only this algorithm will converge to a fair and efficient bandwidth allocation. Okay, so I mean, it's not like that it's the algorithm is still an algorithm. It's just a technique. It's not a ghost who can just magically achieve calculate the rate. It's not some fancy mathematical model or analytical model, but it's an algorithm. It's an ongoing process. So these are the two phases: the AI phase, the additive increase phase, in which the sender keeps probing for more bandwidth from the network, for more usable bandwidth, and keep increasing the transmission rate additively in a careful manner, one by one, and keep noticing if the network is behaving well. That means that my increase in bandwidth is not a problem for network, and the network is capable of sustaining this bandwidth. Okay, and then if in case a problem is being reported, but I don't know, we will see after the algorithm, but a problem can be reported by either a timeout, a packet loss, or maybe duplicate acknowledgements, or maybe extraordinary delays, things like that. Then they will decrease the rate. So then the MD part will be executed. Okay, so multiplicatively decreasing the rate when the congestion occurs. So these are the two parts. Okay, and as I said, all other variants will not be able to achieve this bandwidth allocation. AIMD tries to move towards fair and efficient bandwidth allocation. It's not magic. It's not like that you just run AIMD algorithm and it will just give you a definitive quantitative answer that this is your rate. Okay, your exact window size should be I don't know 6,000 bytes. Okay, we are talking in terms of TCP, so we know that in TCP the window size is not in number of segments, but it's actually in total bytes allowed to be transmitted. Okay, so what I'm trying to say is that running AIMD algorithm is a continuous and concurrent process. So all senders will do that, and all sender will continuously keep running this algorithm so that they keep converging or keep moving towards a fair and efficient bandwidth allocation. And in the last lecture we started drawing this case, and then we ran out of time. So, but I would like to draw it once more by myself before moving to the next slide, in which I have the cleaned up version. So just to draw it by myself over here. So if you guys remember, I again created the toy scenario in which I have, you know, host A, and I have host B, and then they are connected via a router to a host C. And in this scenario, the rate that we have, you can say it's, you know, 1 or R or 1 1 1, whatever. I mean, you take a number or take you can just write R here, R, all three rates are equal. And this was the exact scenario which started our discussion of bandwidth allocation. And obviously, by looking at the picture, we know that the correct rate for A is 0.5 and the correct rate for B is also 0.5, because that rate basically means that both get a fair share, and also the network is not congested, and also the network usage is overall efficient. So everything achieved. Okay. So the problem of congestion control is solved, and the bandwidth is allocated in a fair and efficient manner. So by looking at the diagram, we know the answer, but we want A and B to do something at their own end, to run some algorithm and reach to this 0.5, instead of, you know, someone who is having a look at the network, just like us right now. We are having a look at the network and we can tell that, okay, right, A and B should communicate at 0.5, but no, this is not the luxury that the network devices have. They don't know the situation of other devices, how many senders are connected, how many people I am sharing currently the network with. Okay, so I need to run an algorithm which should just reach to this, you know, this try to reach to this magical number. So the uh, the plot that we tried to achieve was something like that. We had over x-axis, you know, rate of host A, and we had over y-axis rate of B, host B. Okay, and then I started discussing this particular plane, and you know, at the same time lecture time was up, but let's again start discussing from that point onward. So I asked you guys, what is this line? Well, I mean, any allocation on this particular line, if we, you know, just draw a line of exactly 45-degree on this plane, on this xy plane, this all the points on this particular line actually represent what? Any point on this line, any point on this line represent an allocation which is, yes,
XY allocation, sir.
so x is equal to y, right? It's represent an allocation which is x is equal to y, and this correspond to a fair allocation. Okay, so this is a line which is, you know, you can say that a line of fairness actually. Okay, or every allocation on this line will result in an equal division of bandwidth. Okay, and in our scenario, in our simple scenario, obviously there can be more than two hosts. It will be difficult to plot that scenario. We need another, you know, another axis, a z axis, or even, you know, more than 3 dimensions if we have a fourth sender or fifth sender, something like that. But the thing is that our discussion of AIMD will be, you know, conceptually complete even if we understand it on these two planes with only the example of two hosts communicating A and B, and then we can intuitively imagine that, you know, the same will happen if there are more than two hosts and more than two axes over here. So on the 3 axis we can also have a line which has an equal allocation for x is equal to y is equal to z, so something like that. But anyway, so any point on this line is actually a fair allocation. Okay, this line correspond to fairness, x is equal to y, and then last time I plotted another line. So the total allocation can move from 0 to 1 maximum. Okay, it can move from 0 to maximum 1, because we can see over here, you guys can see over here, let me use mouse over here, the maximum rate, achieved rate can be 1. So A can at maximum transmit at 1. Okay, and B also can at maximum transmit at 1, because even if they don't know the rate of this link, the rate at which the hosts are attached themselves have a rate of 1. Okay, so 1 Mbps or gigabit per second, whatever is the rate, or R maybe. So the maximum can be from 0 to 1, 0 to R, and over here as well from 0 to 1. So if I just plot, this line over here, what is this?
So x plus y equal to r.
Yes, we discussed x plus y is equal to 1. This is any point on this line, any point, okay, any point. So for instance, if you take this point over here, the sum will be 1. The allocation of y will be a lot. Y is getting a much more share of network bandwidth. Let's say, I don't know, it's around 0.8 to 0.9 for y, and the rest 0.1 or 0.2 is for x. Okay, so 0.8 is obtained by host B over here, 0.8, and 0.2 is for host A. But overall, I mean, x plus y is equal to 1, so we are fine. This is the line for efficiency. Okay, this is the line for efficiency, right? And any allocation below this line, so I mean in this area, any allocation here, over here, any allocation, any point here is an allocation which is
inefficient.
Yes, but I mean any allocation under this line is an allocation which may be inefficient, may be unfair, but feasible, which means that the network is not congested. But any allocation above this line, so if I take this point or this point or this point, okay, any allocation over here, any point, any allocation point over here is a point where the network will be
congested, sir.
Congested state. Okay, so this is the area of the plane where we don't want to allocate, and this is the area where we can have an allocation. Obviously, it may not be fair and efficient. It may be fair, maybe, but it's a feasible allocation. Okay, so any point over here, let's say it's a point over here, we see that it's not completely efficient because the network bandwidth is not utilized in totality, and it may not be fair as well because x is having just this much here, y is having, I don't know, 0.6, so 0.6 plus 0.2, 0.8 is not equal to 1, but it is feasible. It is not in the congested state. Okay, right. So we have this, and obviously the lines intersect over here, and we know that obviously this point is the optimal allocation. Okay, we want to move towards this point. This is our final goal. This should be our final goal. This is the optimal allocation. Okay, we want to move towards this point. Now let us start from a random point, okay, and run the AIMD algorithm. Okay, now comes an interesting part. Let us start from a random allocation. Let's assume, and before starting, okay, before starting, no, just a minute, let me just see. Okay, I just wanted to see what sort of example is on this slide. So I just want to give a different example so that you guys have both examples. Okay, so let's assume that we start from this allocation. Okay, sorry, let me erase and let me try to, it's not that easy to find right with the help of your finger. Let's assume we start from this allocation. Okay, let's just assume this is an allocation which says that x is having maybe just 0.1 of the rate. You see over here the rate of x is quite less. It's very difficult with mouse. Let me just keep using my finger. So it's like this. Okay, the rate of x, this is the rate of y over here. So y has something like 0.6, x is like 0.1. Okay, let's start running AIMD algorithm. Let's see what happens. So AIMD says two parts, AI and MD. AI part says both senders will keep probing for network bandwidth by additively increasing their rate, their transmission rate, their window size. Okay, so if both senders, if the rate of senders are plotted on XY plane and both senders increase their rate additively, then obviously the resulted increased slope will be on the 45 degree because both are increasing in an additive Okay, so they will keep increasing the rate, something like that. They will keep increasing, and obviously by while increasing the rate, I mean after some time they will cross this line and they will go to the congested state. Okay, and when they reach the congested state, this will be the time, the point when both will be transmitting, and the resulted transmission rate, incoming transmission rate at the router end will be more than the outgoing rate, ingress rate will be more than the egress rate, and if they continue for a little more time, so they violated, they enter the congested region on this point, and they continue for a little bit more time, but obviously soon after that the queue fills up and the loss occur, and then both realizes that the network is in the congested state and they both ran MD part. Now here is the beauty of the MD part. Okay, the AI part takes the allocation towards efficiency and the MD part takes the allocation towards fairness. Okay, so the AI part is here for to achieve efficiency in bandwidth allocation. Okay, the direction of AI part will always be towards the x plus y is equal to 1 line. The direction of AI part, whenever the AI part will be executed, the direction of increase of rate will always be in the 45-degree towards the x plus y is equal to 1 line. And whenever MD part will be executed, the direction of the decrease, the multiplicative decrease, will be towards the origin. And that is what is going to happen right now. So they both realize that the network is in congested state, maybe timeout, packet loss, something like that. And what they will do MD, multiplicative decrease. So multiplicative decrease means that they will both decrease their rate by a multiplicative factor, and the safest multiplicative factor is by 2, divide by 2. So whatever rate you are enjoying, take it to half. So decrease your rate by a factor of 2. So MD part says that the congestion window, whatever is the size of your window right now, okay, that will become C1 by 2. That's the MD part. And the AI part says that the congestion window, whatever is the size of congestion window, is incremented by 1. So you can write plus equal to 1 or C wind is equal to C wind plus 1. Both are right. Okay. So MD part will be executed, and you can see that this is the rate of Y, okay, and this is the rate of X. So if both rates are divided into half, then the resulted allocation would be something like that. This is the rate of X over here. So this rate will be divided into half. So X will move towards something like that, and Y, this is the rate of Y when the congestion happens, and Y's rate will be this. Okay, that is why the MD part brings you to fairness. And why? It's very beautiful that whenever MD part is executed, they both reduce their rate and they move towards an allocation point which is like this. So you notice it's not easy to draw it with. Okay, so you notice that the MD part, the direction of MD part, the direction is always towards origin, always towards fairness, and the MD part is able to decrease the rate in proportionality. So the sender which was enjoying a greater rate has a greater decrease in its rate, and the sender which was enjoying a lesser rate has a less decrease in its rate. So it decreases the rate, it enables, so if both A and B are running AIMD algorithm without knowing each other, without knowing the condition and the transmission rate of the other device, they will act in a how do you say, in a proper manner, महज़िब manner में act करेंगे, ठीक है जी, and they will act for the betterment of network and for the betterment of other senders, and the MD part will ensure that the one who was enjoying more rate will have more decrease and the one who was enjoying less rate will have less decrease. And then again the AI part, and then congestion happens, and then again the MD part, and then the AI part, and then the MD part. And then obviously if we just consider the scenario that there are only two hosts, then finally they will reach towards this point, fair and efficient bandwidth allocation. But as I said, this is not magic, it's an algorithm which keeps running. So they still don't know that this is our optimum allocation and let us stop right now. They don't know that. So they will keep hovering around here, keep increasing congestion, keep reducing into half, keep increasing, keep reducing, keep increasing, keep reducing. But still, I mean, they are in a in a much better position, in the sense that they are having a fair allocation, and it is most of the time efficient, and or it is at least moving towards efficiency. Okay, let's have a look at the cleaned up version, and obviously I want to, and I will be happy to take some questions. So you can see that again the same scenario over here. Additive increase part, multiplicative decrease part, the direction is always towards origin. MD ensures fairness, AI ensures efficiency. This is the line for efficiency, x plus y is equal to 1. This is the line for fairness, y is equal to x, and this is our optimum allocation. These all area is the congested allocation. Okay, and obviously if we start from something else, so for instance I started in my example from this top scenario. Okay, I started from over here, and then I showed you guys how AIMD will reach towards this optimum allocation. But in this example, if we started randomly from this point, for example, okay, and then obviously we keep increasing the rate. So you can see when we reach this point, X is enjoying more rate. X is enjoying that much rate when the congestion happens. Okay, and Y is enjoying that much rate. So MD part will make sure that the rate is reduced in proportionality. You see, so X's rate is reduced up till here. So connection 1 throughput, which was more. So to bring fairness, the direction is always towards origin. The rate is reduced in proportionality, and its rate is reduced like this. So you can say it's bring from 0.4 to 0.2, or maybe it bring from 0.8 to 0.4. So the overall decrease in the rate is much more over here because it was enjoying more. And then again AI part will be executed, then MD, then AI, then MD, and up to so on. Okay. Right. So this was our algorithm, AIMD, and intuitively you can imagine that if more than 2 senders, even if more than 2 senders are running this algorithm, trust me, if more than 2 senders are running this algorithm and they keep increasing their rate additively and they keep decreasing their rate, because multiplicative decrease make sure that the rate is decreased in proportionality. Okay, so they will eventually, all the senders, if they run concurrently and continuously, they will eventually go or lead themselves towards the fair and efficient bandwidth allocation. Okay, is it clear to everyone? We discussed in quite detail, as we always do for every topic, but still if there are any questions, please let me know. This is the AIMD algorithm. Okay.
So